Please.
Okay. Good afternoon, everyone. Thanks for joining me in this seminar. As Fumiaki already rightly said, this is a work in foundational ontology. So the idea we started from was to try and extend the DOLCE ontologies in the direction of digital twins. That was because, we were involved in a project on digital twins, and we were supposed to try to, let's say, disambiguate some fundamental terms so that other partners in the project could develop their own work based on a kind of shared vocabulary. So since in the group of Trento, we've been working on DOLCE for many years. We tried to build this ontology on the basis of DOLCE, on the extension of DOLCE. The work was carried out by myself and Luca Biccari, who at the time was a postdoc on a project that was directing. And he has now moved to the University of Geneva. So since you're all in Switzerland, you can maybe interact with him in the near future, as he's now involved in a synergy grant on digital humanities in Geneva. So probably there are some people you can stumble on in your conferences around Switzerland and Europe in general. So the outline of the talk is this one. The idea, we started from, let's say, a kind of a shared idea in, let's say, in folk philosophy, folk psychology about the digital twins that see them as virtual replicas of physical entities. And we started from this idea trying to show how this concept is kind of limiting to express the properties that we want to attribute to digital twins. And then we started from this, we tried to build the approach based on the ontology DOLCE. The two main, let's say, novelty with respect to the traditional picture of the DOLCE ontology is that we used these two concepts that are introduced in this very work. Well, actually not introduced in this work, but they are adapted from very recent works carried out by Luca Biccari and myself. So we used the notion of aboutness that we developed in a couple of papers that started like 4 or 5 years ago on ontology of mind. And there we studied this notion of aboutness, and we tried to apply it here in this new domain, new with respect to the notion of aboutness. And on another work Luca was involved into that was based on, let's say, ontologies for industry, and in particular for the definition of the notion of dependability. They developed this idea of differential qualities that we have also reused in this paper. So these notions are quite new also for people who are already a bit familiar with DOLCE, but I'll try to explain them a bit before using them in this very work. So, of course, the first part of our work was to consider the literature that is available on digital twins, and then, one of the first features that are very evident from the literature is that digital twins can be, they are a representational object, but they can represent very different kinds of entities. So they can represent both living and not living entities. They can be applied to entities at very different scales, ranging from the microscopic like cells to the mesoscopic like a human body. For instance, they're very much used in medicine to simulate the behavior of individual patients. And also to the macroscopic level, the very macroscopic one, like galaxies, we can use digital twins to simulate what is happening in the space. Or we can also have digital twins as simulation of events and processes, even though in this work we are restricting ourselves to the, let's say, to objects or endurance, and we are not applying this at the moment to events and processes. But the idea is that this is also extendable to these two kinds of entities. And there is another interesting property that we have not dealt with directly in this paper, but we are going to consider in the near future. So the idea that very often we have complex digital twins that are aggregates of smaller digital twins. So for instance, one of the typical application of digital twins is smart cities, and in smart cities you can have the representation of, let's say, parts, components of the city that are themselves represented as with digital twins. And another very obvious characteristic of digital twins is that they're a kind of paradigm. So they are not linked directly to a technology. So you can have digital twins that are based on sensors, digital twins that are based on, let's say, symbolic AI, or also sub-symbolic AI, machine learning. So obviously lately, most of them are really, let's say, embedded into the machine learning and deep learning particular domains, but this is not compulsory, and very likely, at least in my view, the hybridization of machine learning and symbolic AI will be the next, let's say, step that digital twins will reach, probably, as, let's say, artificial intelligence technology in general. So this seems to be the direction. Okay, so another interesting feature that you can find very often in the literature is that digital twins are twins of some, let's say, physical twin, but physical twins not necessarily are actual entities. They can also be potential, in the sense that the digital twin can be used both in the, let's say, design phase, and in this case, you can use the digital twin to direct the building of the physical twin. And so in this sense, the physical twin is seen ontologically as potential, or they can be used to monitor some physical entity that is, I mean, behaving in some way in the world. And in this case, the physical twin is actual. And also they are kind of simulative technology. So they have many features in common with models and with simulation techniques. We can say that they, in a sense, the most developed digital twins are based on both technologies, on both paradigms. You can have models, so in the design phase, and simulation most often at the runtime. And of course, this means that they are not static representations. So they're not, let's say, what we were used to model in the traditional ontology community, but they are dynamically updating entities. And the feedback loop of continuous calibrating mechanism that synchronize the digital twin with the physical twin is something that is very central and important to model. And also the functions that we want to simulate with the digital twins are very varied. So in a sense, they're used to represent the whole life cycle of the physical, of their physical counterparts. So they can be used in all these tasks, or in some of them. So they can be used for designing the design phase to approximate the qualities that we want the physical twin to possess. They can be used for monitoring the behavior of the physical twins, for predicting what the physical twins is going to do given certain conditions, or to prescribe certain kinds of behavior to the physical twin. So for instance, the digital twin can simulate what happens in particular conditions and decide that we don't want the physical twin to find itself in that condition. So we modify the behavior and prescribe some particular actions so that the physical twin doesn't run risks that we can predict by looking at the digital twin. So this is a very brief introduction, just to show how many are the uses of the digital twin, and why, for these reasons, it is important, in my opinion, to have let's say a very well-founded representation of digital twins, because the digital twins that are meant to be used in different tasks are often built using different conceptualizations. So the idea, at least in our view, was to try to give a very general representation so that all these different tasks can be represented by specifying the general representation of the digital twin that we're trying to offer. So why the notion of copy is not adequate to represent, to describe what digital twins are? The first reason is a very trivial one, because it's impossible to store all the information about a physical entity. So what the usual notion of copy is not adequate to represent the notion of digital twin, because in digital twin we very often disregard some properties or some specific aspects of the physical twin. So it's not a real copy in a strong sense of the physical twin. But also, let's say this is to say that the notion of copy is too rigid. But even if you weaken this notion of copy, it's not that we are interested only in some particular aspects, but we are interested in aspects that are strongly connected with the intended task that the physical twin is meant to perform. So, for instance, if we simulate with a digital twin a turbine, and we are interested as a task in failure prevention, very probably we are going to simulate in specific details all those qualities that are concerned with the dynamics of the turbine, of its behavior, of how the friction affects the behavior of the turbine, and probably we will be less interested in some let's say structural property of the turbine, or for instance in the color of the turbine. So the qualities that we are going to select, the quality of the physical twin that we are going to select to build the digital twin, are really tailored to specific intended task. And another interesting thing, not interesting, but a puzzling thing about copies that is not, that makes it not adequate to describe the notion of digital twin, is that if we use the notion of copy, and as we have seen, we can use the digital twin either at the design phase or in the runtime, it's not very clear which one between the digital twin and the physical twin is the copy of the other. Because in a sense, if you build first the digital twin at the design phase to decide how to then build the physical twin, it seems that the physical twin is the copy of the digital twin and not vice versa. So the notion of copy is, let's say, is too egalitarian, if you want, to explain the relationship between the physical and the digital twin. But there are other reasons for which, again, this notion of copy is too rigid, because the digital twin is created with specific purposes in mind. So there is a kind of goal-oriented dimension that is very strong in digital twin, and that is not trackable into the notion of copy. And also the digital twin is agent dependent, which is not always the case for the notion of copy. You can also have copies in nature. But we are interested in something that is goal-oriented and agent-dependent. And we are not, as I was already anticipating while describing the functions of the digital twin, we are not only interested in the descriptive dimension, so in knowing what digital twins are, but also in the prescriptive dimension, so what they are for, why we build them. And they're also a kind of in the everyday use, they are reified in the sense that they are treated as full-fledged entities. So they're not only copies of something else, but in some tasks they use just a substitute of the physical object. So as really first-class citizens of the domain of analysis. For instance, in industry, very often the digital twin needs to be represented in the same model as the physical twin. So it's not simply a copy. So the two basic assumptions from which we have started to to analyze this notion and trying to model it with DOLCE is that there are two important aspects that we want to represent, with our model. So the first one is that the representation relation is the fundamental link between a digital twin and the physical entity that it carries information about. And we have a relation in, let's say, the philosophical literature that resembles this kind of link. And this is the relation of aboutness, of which I'm going to talk a bit in a moment. And then there is another dimension that is very present in recent literature on digital twin, which is the fact that they are considered as steering technologies. So steering in the sense that they, that they guide how the, let's say, how the behavior of the physical twin should be displayed. And so the goal-oriented perspective itself is what makes the digital twin, in our opinion, a steering technology. So these two properties are very important for as a baseline on which we build our model. So we have started, of course, since we were interested in using DOLCE, from the notion of physical artifact, which we will call here material artifact, just to be a bit more understandable. I mean, we are interested in the materiality of the physical artifacts. And physical artifacts in DOLCE are considered to come into being when an agent intentionally selects a physical object and attributes capacities, so there are certain kind of qualities to it. The definition that you can find in this paper by Borgo et Vieux of 2009 is that the primitive notions on which the definition is based are constitution, so a material artifact is constituted by some physical object or some, let's say, amount of matter, for instance. And one other important notion for the definition is that of capacity, which is modeled in DOLCE as a space of individual qualities. So it's a kind of, let's say, a conceptual space that puts together many basic qualities that together constitute the capacity of this artifact that we are going to build or select. Because in DOLCE we not only see artifacts as something that is created by human beings, but human agents, but also something that is used in some way by human agents. So, for instance, if you take a pebble and decides to use it as something to keep paper on your desk, this is not, you're not inventing the pebble, but you're using it for a certain purpose. So you're selecting it in the environment and use it for a specific purpose. So in which sense this intentional selection is also central. So this is the third quality which is important for the definition of material artifacts in DOLCE. So I was saying the primitive notions on which the definition is based are constitution, capacity, modeled as a space of individual qualities, and intentionality, which is used to characterize both the act of selecting an entity and the attributing of capacities. So in the example of the pebble, we select a definite pebble and we attribute to this pebble a certain function, that is that of keeping the paper on the desk. For instance, when I have open a window and the paper risks to go away from the desk. So in DOLCE you find this definition of physical artifacts. So X is a physical artifact if and only if there exists an event of intentional selection, which is E. And in this event we have the participation of the agent, which makes the selection, which is in this case is the Y of the definition. Here I'm just putting the bare definition, but of course in the paper all these things are explained. And this selection is directed towards a physical object, which is in this case P, and the selection is made on the basis of a quality Q that the agent Y attributes to this physical object P. And this makes this P the physical artifact X. So the attribution of this capacity is also what accounts for the steering role of the digital twins. So we select this object because we attribute these capacities, and these capacities are those that will, in a sense, guide the construction of the digital twin in order to make it able to attend to some specific task. Then the successive step of the paper is to specify a bit more this is something that is already present in the past literature, but we decided to use this notion of technical artifacts, which is a small refinement with respect to the notion of material artifact that was carried out in a paper by Borgo and other colleagues of Delft in a paper of 1214. And there they defined a technical artifact as a physical object which an agent or group of agents, so of course the designer can be more than one, creates by two possibly concurrent intentional acts. The first is the selection of a material entity as the only constituent of this technical artifact, which is something that was already present in the definition of material artifact, and the attribution to this material entity of a technical quality. So that was, let's say that this definition was introduced because they had the necessity of using the notion of a material artifact in industry. And in this case, these qualities cannot be qualities whatsoever, but they have to be quality that, in a sense, allows this technical artifact to perform some task in technical domains. And then we come to the notion of information entities and aboutness. So information entities, so we are seeing digital twins on a side as artifacts, then on another side as informational entities. So information entities are meanings or ideas or documents that are about something. So about in the sense that they represent this something. So aboutness accounts for the representational power that we attribute to digital twins. And also the representational character is part of this idea of making the digital twin a steering technology, because one of the technical qualities which, let's say, define the digital twin, the individual digital twin, is its representational character. So the qualities of the physical twin that the digital twin wants to represent. So, in short, an information artifact in this view is a technical artifact which represents or is about some other entity. So, from technical to information artifacts is the following step. So, information artifacts embed agents' intention. So, we want to say that information artifacts are about the physical, about a physical entity. But they're not directly about this entity, in the sense that we didn't want to simply say that a digital twin is like, or an information artifact is like, that a digital twin is an informational entity on a par as, for instance, a book. In the sense that we need something more to say that the digital twin is about this specific physical entity. The idea is that this aboutness, in the case of digital twins, is indirect. So information artifacts embed agents' intention, and in this way they carry intentionality, but they don't carry intentionality directly. They carry intentionality by means of an agent, in this case the designer or the creator, that serves as a link between the representing digital twin and the represented physical object. And we used to, let's say, to put together these three entities, the physical twin, the digital twin, and the designer, the encoding relation that indicates that the aboutness of informational artifacts is not intrinsic. So it's not the, let's say, it's not the same aboutness that we use for mental states, to say that a mental state is about something in the word, or about is not the same aboutness that we use in language than to say that, for instance, a symbol is about some kind of referent. It's something more articulated and indirect. And in order to do this, we introduce this encoding relation, as I will show in the, let's say, in the slides on the former part. And the encoding is possible insofar as the physical object or part of this physical object that constitutes the artifact is arranged in a way that makes it cognitively accessible to some, let's say, human being, or, well, not necessarily human, let's say intentional being. And as I was saying, the other important concept that we have reused in the definition of digital twins that we are going to present is that of differential quality. And differential quality is a notion that is taken from engineering, and it is used to, let's say, put together two perspectives on causation in engineering. In engineering, we have probabilistic approaches to causation that are, let's say, that work at the type level. So, for instance, you want to single out those qualities that probabilistically contribute to produce a certain behavior, and this is more based on, let's say, on inference. And there is another notion of causation that is more mechanistic, that is used also in engineering, and this is usually more connected to explanation of the behavior of artifacts, and it is usually used at the tokens level. But recently, there are a group of scholars, of which I think Williamson is the most well-known, have tried to put together these two approaches to give an epistemic theory about causation in engineering. And let's say that this is used to show how a quality contributes both mechanistically and probabilistically to change, so from a causation point of view, to change the property of another object. So just to give you the intuition for what we are going to do with the physical twin here, the idea is that we are trying to single out those qualities of the digital twin whose changes will cause some, both mechanistically and probabilistically, some changes in the physical twin. So we want to have a connection that is not only representational between the digital twin and the physical twin, but also causal. And we are reused some notions taken from engineering to give this, to put causality into the picture. So aboutness, starting from about, we're going to go in more detail into aboutness. We have started from, as I was saying, previous work that we did in the philosophy of mind, and there we tried to single out by using DOLCE as usual, for us, let's say, two different notions of aboutness that we can find in philosophy of mind and language. Let's say that when we say that, for instance, a mental state is about some content, we can have two ways in the philosophy of mind literature to talk about aboutness. The first one can be seen as a kind of a mental state being directed towards something, and this something is not necessarily existent. So you can think about a belief about Pegasus. You can hold a belief about Pegasus even if Pegasus doesn't exist. So this is what we have called in this paper of 2020 aboutness 1. Aboutness in the sense of being aboutness and intentionality, let's say, of being directed towards an intentional content. But there is another notion of aboutness in the literature, which is, let's say, the one that is also mostly used in the philosophy of language, that is the fact that something is let's say, the referent of a mental state or of a linguistic entity. The reference is something out in the world. So the content, let's say that the way in which we have tried to put together this notion of aboutness, so the referentiality one. So for instance, my fear of the dog of my neighbor has a referent outside in the world, but still, I mean, there is an aboutness relation between my fear and the dog. But as you may understand, there is a difference between the being about that is directed to an intentional content that is not necessarily existence, like in the case of Pegasus, and the referent that is something that is outside in the world. So the way in which we tried to put together these two things in that paper was that we saw the content like a kind of concept in DOLCE that may classify an external reference, so a physical object or a physical event outside in the world. But this is important because while, let's say, aboutness one is necessary for mental states, so mental states is necessarily about something in the first sense, so it has a content, not necessarily it has a referent. And this, as you will see, is kind of useful for us to be applied to the case of the digital and physical twin. So as I was saying, we started from the notion of encoding. So we started trying to trace a link between a link from the representational side of the, let's say, of our task, from information from the information artifacts, the digital twin, and the and then, let's say, and the step back. The encoding relation is what allows us to apply, let's say, the aboutness one in the case of digital twins, because we introduce the fact that there is an intentionality of some kind that is indirect. So information artifacts. So here we are trying to pass from, let's say, technical artifacts to information artifacts. So first we have seen technical artifacts as a specification of material artifacts. Now we are seeing information artifacts as a specification of technical artifacts. So information artifacts are those technical artifacts which encode information which is cognitive graspable by an intentional agent. And so there is a relation of aboutness one between the mental states of an intentional agent and, let's say, the information artifact. The physical object or part of it that constitutes the artifact functions as a symbol. So in this case, in the case of the digital twin, let's say the information states of the digital twin, but seen as physical patterns, acts as a symbol. So even though we can look at let's say, the physicality of the digital twin, because the digital twin is also implemented somewhere, this physicality also has a representational power, which is in this aboutness. So the first axiom that we have used to treat this notion of digital twin is that of encoding. So if we have a relation of encodes between two entities, x and y, at the time t, x is a technical artifact and y is what we call a concept in DOLCE. So it's something that is like an intentional content in the case of mental entities, and this happens at a certain time t. And so aboutness, as I was saying, can be seen as a relation to a content or an object. Let's see how this applies to our specific case. So many information artifacts only need to appeal to this first kind of aboutness, a relation to a content. For instance, if you have a book about fictional characters, you don't need to have a referent, so you don't need to have the relation of aboutness 2 coming into play. While this is not the case for digital twins. So there are other information artifacts for which we need also the, let's say, the notion of aboutness too. So in the most general cases, we have that X is an information artifact if and only if X encodes some, let's say, concept Y, which is at a certain time t, and there exists a mental state Z, that is a mental state of an agent, which is about this Y at time t. So we must have, as I was saying, because this is a kind of indirect intentionality, an agent that grasps the content of what the information artifact encodes as a content. However, there are cases, for instance, like that of digital twin, in which such content can refer to something in the world. So the notion of aboutness too needs to be used as well. For example, for medical records, dashboards in industrial settings, and digital twin. So, for example, we have this example taken from the engineering domain. Consider a digital twin of a rotor, including a parameter for the rotor's orientation angle, so a quality Q that inheres in the digital twin. The digital twin participates in a simulation event, E, during which it predicts the friction due to dust accumulation. As a result, it updates the value of the angle Q prime inhering in the actual rotor. So by simulating the event in a digital twin, we see that there is a certain kind of friction that can cause damages. So as a result, we update the value of the angle of this rotor in the physical twin so that the physical twin doesn't incur into malfunctioning. So the update of Q, which is a quality of the digital twin, causally triggers an adjustment in Q prime, the physical rotor's orientation, mitigating dust buildup. So Q, which is a quality of the digital twin, can be said to be a differential quality, the one that I introduced previously, for Q prime, which is a quality of the physical twin. So the simulated event E serves as a satisfier of an instrumental goal G. So there is a goal, and the goal is probably, let's say, that of, in this case, of reducing the dust buildup in order not to have a problem with the friction. And the satisfier of this event is this goal is the event of changing the angle of the rotor. So changing this angle makes us reaching the instrumental goal, the instrumental goal. So the occurrence of this event E, the change of orientation in the angle of the rotor in the digital twin, brings about an event E prime in the actual world that in turn satisfies an actual end goal G prime. So we have a goal outside in the world. So we have a goal with respect to a physical twin, an entity in the world that we want to behave in a certain way. But in order to have this, to reach this goal, we need to understand what we have to do. And to understand what we have to do in the world, we simulate something in the digital twin that makes us understand what we have to do then in the real world. So that's why here the notion of differential quality is important. So to put it in formulas, we drew this axiom too. So we have an event E that causally contributes to an event E prime when there is a quality Q and a quality Q prime, and Q, which is a quality of the digital twin, sorry, not queen, is differential quality for Q prime, which is a quality of the physical twin. So both the digital and the physical twin are endurance. And okay, the qualities are qualities of the linear Q, respectively Q in X, which is the digital twin, and Q prime in X prime, which is the physical twin. And the physical twin no, sorry. And there is some participation of, what was Z? Sorry. Okay, we haven't put Z in the, probably was in. Okay, sorry. I think that is a mistake. So the axiom 2 states that if E causally contributes, so if the event E causally contributes to the event E prime, there exists a quality Q and a quality Q prime, such that Q is the differential quality of Q prime. This means that a change in the value of Q brings about a change in the value of Q prime. These qualities inhere in the endurance X and X prime respectively, with X participating in E and X prime participating in E prime. So the Z should have been an X, sorry. I corrected the slide before putting it online. At this point, sorry, we are ready to have the definition of digital twin, which looks kind of complex, but I mean, should be now built on the premises. So the axiom 3 characterizes a digital twin X as an information artifact, depending on a physical endurance W. So we don't know yet what is this physical endurance is. We are not calling it physical twin yet. Moreover, X participates in an event E, which satisfies an agent's instrumental goal Z. The event E causally contributes to the event E primes, which satisfies the agent's end goal. So, in other words, we have that the digital twin participates in an event, let's say in the digital domain, which satisfies an agent's instrumental goal, which contributes to the, let's say, to the satisfaction of another goal, which is in the real world, not in the digital one. And this is the definition of digital twin that we have given. And after that, we can also define what is the physical twin of a digital twin. So the physical twin is a physical endurance, and this physical endurance is a reference of an information content which is encoded by the digital twin. And this renders, let's say, the indirect aboutness of the digital twin. So we need, let's say, the content of the digital twin. So if we see the digital twin as, let's say, an information, an information object which has, let's say, a physical substratum, we're interested in seeing the relation between this physical substratum of the digital twin, the content of the digital twin, which is something, let's say, abstract, and the physical twin, which is outside in the world. So axiom 4 says that if a physical endurance is a physical twin, then it is the reference of an information content encoded by the digital twin. And this should render the fact that an entity becomes or plays the role of a physical twin only when it has a digital twin encoding a content to which an agent directs their mental state. So something in the world is a physical twin only if it has a digital twin. So it's a kind of a reverse the relation with respect of what we are used to see in the literature. So concluding, although there is existential dependence between the digital twin and the physical entity, so sometimes, as I was saying, the digital twin depends on the physical twin because it's a reproduction of it that is used to monitor, for example, the behavior of the physical twin. Sometimes it's the vice versa. So there is a dependence of the physical from the digital when the digital twin is used, let's say, in the design phase. Aboutness is the main relation linking the two, as the digital twin carries information about the physical twin, and this is not reversible. It's always, of course, it's obvious as it is, but it's always the digital twin that carries information about the physical twin. And digital twins are information artifacts that are always connected with the material entity with the relation of aboutness to, on which they exert a causal impact. And this is given by the differential quality relation. Not only intentions of the designer matter, but also those of all the agents who can grasp the information they encode. So this introducing this indirect notion of aboutness, in a sense, makes into the picture, puts into the picture also the agents that are going to use the digital twin. Then future issues. Here in this paper, we are considered, in a sense, only digital twins that are, let's say, individuals. So that are a simulation of individual physical objects. But of course, the study of a prototype digital twin, the one that is thought to, let's say, to reproduce, for instance, a kind of phenomenon. So not an individual occurrence of the phenomenon, but the phenomenon in general. This has, I think, different properties that need to be rethought in order to have a model of the prototype digital twin. And also another thing that I believe deserves to be investigated more is this relation of dependence. What happens when we reverse the dependence relation? So maybe the formulas have to be, let's say, specified for both cases. We cannot, and maybe one of the two has to be changed a bit in order to render both the case of the digital twin that comes into place at the design time or at the runtime. And okay, this is was the third question. What happens to causality when the digital twin is used at the design phase? So probably we have to reverse our notion of differential quality. So it's not always that the differential quality of the DT is of the digital twin is what changes the quality of the physical twin. So this is something we still have to investigate with more detail. I will have given you some reference at the end of the presentation so that you can see the papers in DOLCE in which these notions are introduced, because I understand that giving a half-an-hour presentation is a bit strong, but you can find these notions in these papers. I haven't put the paper in which they have presented, but I will give the let's say the exact reference to Fumiaki to put together with the presentation. And I finished. Thanks.